Thank you all. Excellent presentation by Al. Thank you. Lots of great stuff there. We're not going to be going into so much detail in terms of the actual cracks. And so, you know, obviously failure mechanisms are looked at in different ways, but this one's not going to show all those nice little cross sections. It's going to be a little bit more about system and about data and operation. I think the topic, hot reheat bypass cracking or turbine bypass valve cracking in general, is something that I think many of you in the audience have experienced on your own or have heard about before. You know, we're stepping a little bit outside necessarily the HRSG. You know, we're going a little bit further out, but I know Bob's included bypass valve studies in some of the seminars in the past. And so I think it's still great for this audience. My name's Ori Selzer. I work for IMI CCI. I'm the application engineering manager there. And then, yeah, Diedrich was going to join me on this. And if he can get in, I'll let him introduce himself, or Adrian, who is the plant engineer at Goreway. And Diedrich is based in Calgary at the corporate offices for Capital Power. So the way this presentation will flow is just some introductory stuff in terms of what's the plant, what's the application, and then what are the failures that were experienced. And then from there, it's going to get into kind of what are the steps after the failures, and what steps do you take to repair and ultimately mitigate or, you know, stop this problem from you know, continuing at the facility. So again, this was at Goreway Power Station. So it's a 3-on-1 combined cycle. It's got a air-cooled condenser. It's located outside Toronto, Canada, purchased by Capital Power in 2019. I do know it's got some, you know, an interesting call out for their gas turbines there. And I know if people are curious, they can ask about that in the Q&A. And I'm sure if Adrian or Diedrich are on, they'll be able to give you some more information about that.
Ori, can you hear me?
There you are. Yeah.
I had to jump offices. I'm in Adrian's office. Okay. All right. Did you get through this entire slide? I'll just point a couple things out.
What are you right now?
All right, perfect. I just wanted to point out in here, you can see from the photograph on the right-hand side, you'll notice the CTs out front, and you'll see the bypass stack and the HRSG outlet stack on the back. And one thing you'll notice is that all three HRSGs are inside a powerhouse, fully contained and enclosed. That's a little bit different than a lot of plants I think that people would have seen. And then on the left-hand side there, you'll see the air-cooled condenser. I'm not sure if you mentioned, Ori, that the EPC on this plant was SNC Lavalin. So just in case, as we get into this, if anybody else does, maybe some of the issues could be potentially common. And then the final comment there, of course, is that Capital Power acquired the Goreway station in April of 2019, and so it's just a few years ago now. So that's the bit of the background about the Goreway plant.
Thank you, Diedrich. There's a little bit of an echo. Maybe on your side. Let's see if it's gone. Great. And can people see my mouse? Can somebody give me like a verbal, Bob, maybe, if you see my mouse movement?
You're all good.
Yeah, I can see it. See
Perfect. Okay, great. So thank you, Diedrich. So that's kind of the plant setting. And then let's just set the stage on this application for anybody in the audience that's not aware. I mean, typical combined cycle is going to have your 3 pressure bypass systems, your HP to cold reheat, your hot reheat to condenser, and your LP bypass off the boiler dumping to condenser. So we're specifically focused on the hot reheat to condenser application here for this specific presentation. But of course, some of these problems can also occur on your HP to cold reheat, not so much on the LP just because of kind of the temperatures and the pressures that it lives at, but definitely on either the HP to cold reheat or the hot reheat to condenser. You can see these issues. You know, these valves are just there to route steam around the steam turbine, either during startup shutdown or during a trip event of some sort. So, you know, they're going to see, they have the ability to see 1050 or max temperature hot reheat steam in this case at full pressures, and then dump that into the condenser. Now, couple just, you know, again, I could go off for hours on turbine bypass, but I just wanted to highlight some critical things as it pertains to cracks and failures. I mean, the hot reheat bypass system is the largest of these, just by the fact of the volumetric change that you're seeing when you're going to condensers. So, you know, these valves, typically they can see 16 to 20-inch inlets, you know, 24 to 42 or even bigger on the outlet, just depending on what it's dumping to. So very large valves, 12, 14, 18-inch trim sets inside of them. They also have the highest temperature differences when you're looking at the steam coming in, 1,050 degrees, to the water that's being used to cool that steam, which in the majority of plants, and well more than 50%, like 99, or the majority of them, are using condensate. So it's even colder than, you know, boiler feed water that might be at 250, 300 degree Fahrenheit. You're talking a lot of times down at, you know, 120 degree Fahrenheit. You're looking at major differentials, 900 degree Fahrenheit here from that water to that steam. And that's going to be critical when it comes to some of the driving root causes for these cracks, which is these thermal stresses that build up from that big differential. And then also note that the hot reheat is dumping to condenser. So the percentage of water being sprayed is a massive amount, upwards of 30% by mass of water to steam. So you're putting huge amounts of cold water, think massive fire hoses of cold water spraying into these systems to cool it down to ready that steam for the condenser. So that's kind of just setting the stage for the application. Now trying to dive a little bit deeper so that you can recognize what is happening at Goreway and their installation. Now Goreway is a bit unique. It's an air-cooled condenser system. And so those can take some unique installations in the sense that, let me just highlight first, again, could talk ACCs for a long time, but ACCs operate at a lower enthalpy than a typical water-cooled condenser. My understanding is this is because of the expansion joints in the large ducts in the ACCs. So when bypassing to an ACC, we have to cool the steam down even lower than a water-cooled condenser. Typically, this means we end up spraying to saturation prior to entry into the ACC. So many times you can't run saturated steam through pipes around elbows. So installations will use a two-stage superheating, and that's what Goreway has. So Goreway has the initial steam letdown valve, the hot reheat bypass valve, a 16 by 24 steam valve with its associated superheating system attached right with the valve. So you see that here, there's a 16 by 24 expansion incorporated in the outlet of this valve. So steam comes into the 16-inch and then expands to 24 through this diffuser. And this is a very common piece in many turbine bypass valves, are these diffusers that are in here. And that'll be common, and we're going to see more of that in the presentation. Those diffusers are there to not only break up the large 16-inch jet and quiet it down, but they're also there to prepare the steam for injection of water. So the steam is routed out of this diffuser into this annular region and then expands, and we can inject water in this location and get good mixing of the water and the steam. So again, just pay attention to this diffuser because that'll come up later. Now, again, what's unique about Goreway is they have a second stage spray system further down the line, gosh, about 75 meters maybe or more down the line, right before the condenser entry point, basically. So this is the desuperheater where they will be spraying to the saturated levels. So they're quenching to saturated levels. There's a straight shot from this desuperheater right into the connection point into the ACC duct. And then at the ACC duct, this is a low noise ACC duct dump system. So this actually has one of our multi-stage drag resistors, a 16-stage pressure reduction resistor that is actually handling that steam as it's expanding into that duct. So it has to go through this device as it expands. Many of you maybe are more familiar with what we refer to as a dump tube, which is just a drill hole cage, something that looks a lot like this diffuser. That would be a higher noise system, but I just wanted to highlight here in this system, this is the duct dump device, and recognize there's 3 of them. It's a 3-on-1 unit. So this kind of duplicates itself on unit 11, 12, and 13. So hopefully that kind of sets the stage for the application, the specifics of this. Now, we will be focusing only on the first stage part of this system. So everything we're going to be talking about from this point forward is associated with what you would refer to as the hot reheat bypass valve and its desuperheater. You may see sometimes it's referred to as the first stage desuperheater. I'll hand it back to Diedrich, and he's going to be able to highlight kind of the failures, what happened here, and set the stage.
Sure. Can you hear me okay?
Yep.
Okay, great. Yep. So what you'll see, the first comment is very, very early in life. There were issues with the internal existing liner, and those were actually removed and taken out.
And I'm circling them right now, just as he's talking. These
Perfect.
Yeah, you'll see these here.
That right there. Those were removed very early in life. Again, before Capital Power had ownership of this plant. But what we then suffered repetitively were these cracks that are identified here. You can see the nozzle to pipe and the manifold identified as A, and you can see the manifold attachment to the nozzles, the cracking that we're seeing as well. And so obviously, given the significance and the severity of all the cracking, the decision was made to replace this section of the outside pipe portion with the nozzles and the manifold. So this was our planned scope as we came into a recent turnaround.
And I'll highlight one thing here too, Diedrich, is that some people in the audience may be familiar with failures at the downstream kind of girth weld here. That was not the case at Goreway. So that weld was not seeing the problems. It was these welds. And
correct.
And then when you get into that base material, it just becomes very challenging to try to get into this area and repair. And that's where, if you do one or two repairs on small cracks maybe, but once they had such a large crack around, that's when it was deemed that you had to just replace. Yeah, exactly.
Yep.
Go ahead, Diedrich. There you go.
So there's the description of the new component. Like we said, it was the outer pipe, the nozzle, and the manifold. We bought this as an entire fabricated spool. Now, the really interesting thing happens here is that once we cut the pipe off to gain access to make the spool replacement, when we removed it, I know that looks like a perfect end piece missing on the diffuser pipe there, but there's an end cap that is supposed to be there. And when we removed the pipe, that end cap was already gone. It's on an earlier slide. You
Yeah, here I
can
can.
in
Here it
the
is.
drawing, right? Just
It's
right.
this hemispheric welded on cap. Yep.
Right. So, but when you look carefully, where it actually broke was through the ligament of the holes in the diffuser. It kind of started propagating and cracked all the way around, and then liberated with a piece of pipe with some of the diffuser pipe and the end cap. What you'll also notice up close where Ori was had the mouse there for a second is you can see the amount of erosion that was really visible around the holes. So again, this was another telltale of what was happening in here from a damage perspective. So in this case, we had to go back to the drawing board a little bit and plan subsequent replacements we modified the diffuser, and we can get into a little bit from the distance from the spray nozzle to the cap, but we made a bunch of changes to this component and made an upgrade design, which is what we're currently working on installing.
And I'll just note that this photograph is the ID for those that are interested. This erosion was on the ID of the diffuser, not the OD. So, yep. And then this is go ahead, Diedrich. This is kind of that new diffuser design there.
Well, exactly. So there it is. Yep. And we actually sent one back, and it got modified. All the upgrades were made in the component, and maybe part of my IT issues is I'm actually at the plant right now. We are in turnaround, and we are currently going to be installing this final temperator. Even hoping to lift it up in position tomorrow. So this is all happening for us real time.
Yeah, so two of them have been in, and then this will be that final one on this on unit. Is it unit 13? I think that's going in there.
13.
Yep. Great.
Yeah.
Yeah. So that highlights kind of the what happened there, just the history of the cracks around the nozzle connection points, but then just this all of a sudden wow, what do we have inside this other major failure that needed work? And so at that point, once the diffuser specifically was found to be failed, we really had to look into that. So first we worked on, again, as Diedrich mentioned, we made a new upgrade design that incorporates not just the spool, but it brings in the whole diffuser so that they have a brand new diffuser. And of course, the original design of this system was done, I think 2007 or so, so about 15 years old. And we are always continuously making improvements on our design. So throughout those 15 years, we've found things that have helped to mitigate and reduce failure points. So we incorporated some of those in the upgrade to this system. You'll notice first we used to make kind of these transitions out of welded joints of material, and now it's a single forged piece of material that handles the 16-inch connection to the valve and expands to the 24-inch connection on the spool pipe. Another key one, we know that there was that photo showing failure at this weld. This is one of the few places, attemperators to superheaters are one of the few places where you connect water piping, directly to main steam lines. I mean, drain valves, you could argue our drain lines are similar, but we talked in the first presentation about movement of these things. So what we've found throughout the years, you'll see over here, short water legs, only about 12 inches center line to center line, that if we increase those, throughout the years, we've reduced the amount of cracking at the joint here. So that upgrade was part of it, longer water legs. Also over here, the older design, we had something where, we used to align the inlet connection with a nozzle, and it turns out what you ended up doing was creating an even shorter leg just in that one location, which led to failure there. So the new designs, we would no longer connect individual water nozzle right into the connection for water supply. So now you have an independent supply that's kind of rotated between two nozzles so that it would never have that third pipe connected to it. A couple little things, you'll see a little bit better transition here to kind of smoothly transition both from a flow, somewhat from a flow profiling in terms of the fluid dynamics and separation, but more so just to make this joint a little safer too from stresses, to have a more gradual transition into this weld location, especially with that erosion that was being seen. If there was thinning, we didn't want to stress that other connection there. And then obviously the new design came with no liner. That was removed previously, and the site kind of felt that those were a bit sacrificial and they didn't want to have to be worried about that coming apart. So the new design did not incorporate a liner. Now, ultimately, I just want to say that, hardware is one part of this multi-pronged approach that we ended up taking. So once Goreway saw that they had this internal failure, it became clear that we need to go deeper into finding out what caused the problem here. And yes, the hardware will give them some longer life, but if they're continuing to drive it with, I always say like the bending the coat hanger, if you're continuing to bend, then you're eventually going to fail even if you upgrade the metal. And so this led us to kind of work together with the site on some more root cause analysis looking into operation. And so we worked together with Goreway on an IMI Insight study. And IMI Insight is our prescriptive analytics branch of IMI, where we look at data. We're looking for data signatures that we link to failures. We've been looking at DCS data and this type of cracking for, gosh, unfortunately, almost about 20 years now. And we've got a great feel for what to look for. And so we're automating all of this into software that can load in data. But before I get ahead of myself, basically, what is IMI Insight? It's just, taking your problem, your data, your system, and it's combining it with our knowledge, our history, our experience, and the tools that we have to analyze. And it provides you with solutions that can lead to savings, safety, and overall value for our customer base. And so what did we do here for Goreway in this IMI Insight study? Well, first off, I'll say the biggest difference here is the amount of data we can study. We can study months of data at small intervals. So in this specific case, and most of this work was done late summer into early fall of last year. And we acquired 4 weeks of data 44 weeks of data on all 3 units. So it represented 28 different starts across the 3 units. It was 104 discrete process variables that we were analyzing across the 3 units at 10-second intervals. So you were looking at more than 25 million data points there that we were analyzing. I will point out too that early on in our analysis, we identified that the site's Pi historian was compressing data at a pretty, let's say, a pretty coarse setting, which maybe was there from earlier days when data storage might have been a little bit more expensive and somebody set it up to just not store as much data, where nowadays data storage, especially just small stuff like this, is maybe a little bit cheaper. I don't know, but either way, we identified that because the first sets of data we were getting, we saw a lot of coarse movement of temperatures with, the Pi data was only being held maybe with changes of 15 or 20 degrees Fahrenheit, it would rewrite a new point. And so it was kind of hard to analyze that. So the site had to go in and make all new compression settings. They had to set all that into all the process parameters we needed. And then we had to let the plant run and get the startups after that point. So that was done kind of the middle or early May. And then from that point on, we were able to kind of get in and collect this data. So that tells you what the data set was that we collected. Now, for those of you that have looked at data, how would you start with 25 million data points? How do you visualize that? Are you going to use Excel? Gosh, I think every time you add, I've shown an Excel plot here with 4 different process variables. I think if I were to add a 5th, I would probably have to walk away for about an hour and a half and then come back to let it plot at that many, data points that it's plotting. And then also, even if you could plot it very well, at this point, you're looking at 4 weeks of data. What's important to look at? How deep should I go? Can I look at the 35,000 foot view here and ascertain anything, or do I need to dive in deeper? And again, what I've known from the experience that I've been doing over the last 15 to 20 years of this is typically we don't look at this high level because we can't really see too much. So typically what's done is we zoom in. So we do these strip chart type plots in Excel of just one startup, and then maybe we ask the site, could you get us a hot start and a warm start and maybe a cold start? And we'll try to plot these individual startups and we'll try to look at them. But the thing is, you're kind of saying, okay, I'm going to make judgment call from this one startup. And I don't know if it's always starting up this way, but I have to make those assumptions, or I have to try to isolate each of these startups and plot them. And maybe, over time you could plot 8 startups, 12 startups, but now you have 12 sheets of paper they were trying to look at. And so, how confident are you that you're finding the problem? And so what we've done with our software and our tool is we've tried to make this life easier. We can load in months worth of data. The software will immediately identify startups and shutdowns where a bypass valve is being used, and it'll start isolating that data so you can quickly graph it and see it. And it'll also do some very interesting visualization, such as overlaying them. So as you automate this process, you begin to start to be able to quickly visualize things. Now, there's probably maybe half of the audience that's going to get really excited when I show charts like this, and then there's probably half the audience that is just going to glaze over. So I know I'm kind of walking a fine line here, so I'm going to try to start each of these slides with just high-level takeaways, and then maybe save some of the details for some Q&A for those people that are really, really interested. Feel free to ask some Q&A, but I'll try to give a little bit of detail, but I won't try to lose half the audience by going too deep. But the concept here is we want to find new ways to visualize this data so that we can quickly get to problems. And so this first critical finding from this visualization, what you're seeing here is the hot starts on one unit that have been isolated and laid over each other so that time 0 represents when the bypass valve is initially opened during a hot start. All right, so now you can start to see it wasn't just one startup that had this problem, but every single hot start was initiating over 100 degrees C per minute quench of this first stage, the superheater. And that's shown very clearly by this rapid drop in temperature. Now, it's challenging to plot the saturation temperature because you're looking at multiple startups with varying pressures, so I don't have that, but just take my word that basically all of these were being quenched down to saturation riding saturation, and it's only when they lift that you actually start to regain some superheat. And actually you can see that in the dotted line. So for those that are the detailed people that really want to look into this, the dotted line is the degree of superheat downstream of this superheater. So you can see the degree of superheat is completely taken away on all startup, quenched to saturation, and then over 20 minutes, finally, it starts to heat back up and it tries to land at about 50 degrees of superheat eventually. So this was the first critical finding. Once we were able to isolate all of these hot starts, we realized that every hot start was initiating a massive quench on this system. A deep review of the control logic at site, first it identified some very robust and excellent enthalpy control logic that was put into service at this facility by the EPC. Now, remember, I mentioned this is a complicated system with two different superheaters that have to work together. And it was a very interesting enthalpy control logic that split the spray between those two superheaters to ultimately get the enthalpy that was needed at the condenser. My initial thoughts were there must have been a problem with one of the parameters in that enthalpy control logic, and it was leading to massive amounts of water to be sprayed at the first stage and not enough at the second. And maybe they had it flipped. Why are they quenching to saturation at the first stage when they should be quenching to saturation at the second stage? So that's where I dove in first. But once I ran all of those calculations in our software and got all the flow calculations, we realized, no, it's that part of the logic was doing everything perfectly right. And we had to dig through the logic diagrams to find one simple little override that was put in that said, for some reason, this first stage spray system should limit the amount of superheat to 50 degrees C. And that was overriding all the other control logic. And now when you back up and look at this, you realize, well, every single hot start, we're going to have residual heat in our line. So as soon as we open our bypass valve, you can see the dotted lines. We're way over 100 degrees C of superheat when we initially open the bypass. So the logic kicks to this override and tries to immediately spray down to remove superheat. And it oversprays because at the early stages of startup, there's very low amount of steam. The spray valve sees I'm 100 degrees off of my set point of 50 degrees superheat. It opens a spray valve way high, and it takes the system over 20 minutes to, dry out that water. And then eventually it stabilizes around 50 degrees C. So all this work was done to program some beautiful enthalpy control logic, but ultimately we found that it was this 50 degrees C override that was doing all the control. And realize this is extremely challenging to try to do because you're trying to hit a moving set point. The degree of superheat, saturation temperature will change with downstream pressure. You're dumping to condenser. So as you open your bypass valve more flow is going and you're building up pressure. As you build up pressure, the saturation temperature becomes a moving target, and you're trying to maintain a 50-degree set point on a moving target. Also, the more water you put in, you change the downstream pressure. So you're kind of coupling your variables here. So ultimately, the biggest takeaway from this is if your system is set up to try to limit degree of superheat downstream, you might want to check into this and be concerned about what might be happening there. So this was critical finding number one, that we're initiating massive quenches on hot starts, and we need to avoid this. There's another critical finding, and I have three of them. So we'll go through the second one and then we'll get to the third one, and that'll kind of close out. We'll come back and do a little bit of summary at the end of it. So again, I don't want to lose everybody, so I'll just try to stay high level on this critical finding number two. Just to acquaint you with this chart, what we're looking at now is not the opening, but the closing of the bypass valve on all those startups. So what you see now is time zero when the bypass valve has fully closed. And we've laid all the startups on top of each other. So you get to see these trends now where you can see that this is happening again and again and again. And every time the bypass valve is now closing off, what are we seeing? Well, we're seeing this dip in temperature and then a rise after the bypass valve is closed, and then a decay. And ultimately, what we would want to see is you're controlling around 200 degrees C in the outlet of your bypass station in that pipe going down downstream of the bypass. ultimately, when you close the system, you would want to just see it naturally decay, heading to condenser temperature. If you had a long enough time, that vacuum, I mean, this is a long run of pipe. It's 80 meters or more from the condenser. So it's going to take some time, but eventually if you waited long enough, and we saw this in some of the charts, that this temperature will eventually decay all the way down close to condenser temperature. But why is there this dip, this immediate dip of about 50 degrees Celsius and then this rise? Well, we've identified through our algorithms, this data signature of this dip on closing represents excessive spray of water right at the closing of the bypass valve. And it can be related to control logic issues, or it can simply be a sequencing problem where the water valve stays open just a few seconds longer than the steam valve, and it puts water into the pipe and then cools everything down. So it's this combination of either excess spray right at the shutdown of the valve, or the water valve staying open a little bit too long. Those are both things that can drive this type of data signature. Now, why do we care about that? About a spray valve, spraying excess amount of water right at shutdown? Well, remember, there's this diffuser in here. You have steam flowing through it. As you close the steam valve upstream of this, you're reducing flow. And so if you're slowly or quickly, over the course of 30 seconds, shutting your bypass valve, you're reducing this flow and you keep the water on, then basically what water that was always being pushed downstream by steam flow will now be able to spray upstream. And a diffuser that was sitting at 1,000 degrees Fahrenheit because it's been operating for, depending on a startup, it's been operating for 30 minutes, for an hour. It's heated that entire diffuser up to steam temperatures 900 to 1,000 degrees. Then you close the steam valve, but leave the water valve spraying, and you just quenched that entire diffuser. So this was the data signature that also drives the failures on the internal diffuser. So we have the initial quench upon startup, and then at the shutdown of the valve, we have another quench where the water is hitting this internal diffuser, leading to this type of failure. So, I often mention, the data is kind of the roadmap, and in this case, it's great when we have the problem and then we know what we're looking for and we can immediately find it. But this can also be kind of in the opposite direction. If we identify these signatures up front, we can try to help you avoid some of these issues before they get this bad, if you can see these things and find them in your data. So that was critical finding number 2. And then the last thing was that interesting erosion pattern on the ID of the diffuser that we showed early on. And, we've talked about wet steam erosion in a forum a couple years ago, and it is a topic that Bob has talked about on HP valves. But basically, this is an example of erosion, or let's call it entrained condensate, in a hot reheat to condenser dump system. So again, another chart, not to lose everybody, but I will try to acquaint you with this. You've got the exhaust gas light off, so this represents exhaust gas temperature on the GT. So letting you kind of know where that starts. And then here is kind of initiation of pressure in the hot reheat circuit. So this is the rising pressure of the hot reheat steam coming into the bypass valve. This is the outlet pressure, so you can understand the differential pressure across the valve. And then the green is the demand, and the blue is the feedback for the valve. So the valve, this is a common practice that we see. The valve is parked at 10% during the initial startups here. This was a cold start. And the most important thing here is the gray line is the saturation temperature, and the yellow line is the upstream temperature measurement upstream of the bypass valve. Now, luckily at Goreway, they have a sensor that is maybe a little over 1 meter upstream of the valve in the takeoff to the bypass valve. So this gives us probably the most accurate that I've seen. And I know Bob's done a lot of these studies, and a lot of times you're having to deal with a temperature sensor in the main header. Maybe it's 40 or 50 feet past the T where the steam enters the bypass. But here we have one that is in the takeoff and it's right upstream of our valve. So it gives us an excellent ability to kind of understand that. And what you see here is about 6 minutes of operation where that temperature is below saturation or at least below 15 degrees of superheat, 15 degrees C of superheat. 6 minutes of operation of that just on this cold start. And in our data set, on average, the cold and the warm starts, we're seeing about 5 minutes of operation on every cold start and every warm start where the valve was being exposed to this type of operation, where you're seeing, the potential for condensate to be entrained with steam and leading to the damage. And the site has the, you call it the smoking gun of that. Here, this is again a drag velocity control bypass trim disc stack inside their hot reheat bypass valve. And you can see erosion on an Inconel. We've talked about this in the past. This is Inconel 718, which we know in dry steam stellite Inconel, they live pretty well. They shouldn't erode in dry steam. But this is the telltale sign that you have condensate entrainment. So it's damaging not only the disc stack here, but then it's making its way into that internal diffuser and thinning the wall there. So you have, I guess there's kind of a parallel to the earlier presentation. It's like the ID is being thinned by erosion and the OD is getting hit by water and quenched. So you have these multiple failure mechanisms driving to eventually fail this end cap and break this off this diffuser. So that kind of wraps up the data. I'll give it back to Diedrich to just say, okay, we presented this to Capital Power and our findings, and then they are taking that information and kind of working with that.
Right. Yeah. So exactly as mentioned, we're just now wrapping up the hardware component replacement. It'll happen in this month. So we'll have the attemperators replaced. What we've done, taking all of Ori's findings that he just explained in detail, we've taken all of that feedback on our logic, and we're in the process of reviewing all of that, and just in light of the connecting it to all of the plant controls and logic as well. So, and looking to see what modifications we can make to avoid all of the critical points that Ori pointed out. And then obviously you saw some of the damage and wet steam, and there's some upgrades that we're also looking at for future upgrades on this system as well. So it's all well underway based on Ori's findings.
Yeah, and I think this is one of those where, Bob, we've said this before, where it's like maybe we'll fill you back in, at the next meeting, and hopefully maybe we'll have a face-to-face meeting in 2023, and we can come in and fill you in on that, on the further kind of changes that were made at site. Just to high level summarize before we kick it to the Q&A, I think bypass valve cracking is plaguing a lot of the combined cycles in North America. I would venture to guess over 50% have experienced something like it. And it's one of those, if you haven't yet, it's not if, it's when. And again, it's a multi-pronged approach. I really want to drive home that, yeah, hardware is one part of it, but don't think that if you just put a new piece of metal in there, it's not going to fail if you continue to drive these massive quench events or these operational things. It's a multi-pronged approach. You got to look at the hardware, you got to look at the data, and you got to modify the operation to eliminate the root cause. And they're all unique. I always say the data is the roadmap. We have maybe a dozen different data signatures that we link to cracking, and so we're always looking for those. But then the really unique thing here with Goreway is that suddenly it's this 50C superheat override that just plays this massive role that we necessarily weren't going to find if we were looking at the other 10 that we were used to seeing. So yeah, and then I would just say, and maybe Diedrich can say it best, because it's one of those things where, yeah, go ahead, Diedrich.
Yeah, absolutely. Yeah, no, 100%. Clearly one of the big takeaways here as the plant, you could argue, was approaching the 10-year mark of life, getting in and doing a boroscope and getting inside these components was critical. And as Ori knows, these are by far not the only attemperators we have at this plant. We have a lot of attemperators. So this has just kicked off a much broader and extensive inspection scope to make sure we're ahead of the issues before we find it a little bit more the hard way.
Yeah, thank you all. Thank you very much. Q&A.
The hard way at Goreway. I like that.
Yeah.
Thank you, Ori and Diedrich. I'm one of the 50%, Ori, that's very excited about the data you showed. We have a couple of questions from G. Martin. I'll read them real quick. One is, what's the rule of thumb on how much percentage of water is sprayed in the first stage to superheater versus the second in a system like this?
Good question. Typically for us, we tend to try to control to some temperature on the first one. A lot of times we would try to do a temperature control and just bring it down to carbon steel level, safe levels in Fahrenheit, like 500 degrees Fahrenheit. So we wouldn't do a percentage change. We would bring temperature control down to something like 500 degrees. And then we would do the quench with an enthalpy control logic on the second one right before the ACC duct. So that's the way we would normally do it. That's why I thought this was interesting at Goreway, because they were doing a percentage, and the enthalpy logic was doing 65% at the upstream and 35% at the downstream, just with a simple, a simple coefficient in the logic that just said, calculate how much water is needed, multiply by 0.65 and send that to the first one, 0.35, send that to the second one. So initially I thought, that doesn't look right, and that's the problem. That's probably too much water at the upstream system causing this quench, but it turned out that wasn't the problem. So maybe that's a simpler way, but we tend to try to program them to do temperature control on the first one, then dump to saturation on the second. Maybe that 2/3, 1/3 is.
His second question is, where did the missing diffuser cap end up? I assume found it somewhere.
all the way down the line, right up before the ACC. We don't have the line drawing, the spool drawing, but as Ori said, there's many feet of pipe between this point and the ACC.
Well, the second part of that question was there any operational symptom or evidence that the cap was missing prior to opening the pipe?
None, not a clue. And
So,
some of that we discussed with Ori at the time to take a look, but there was nothing in the operation at all that told us that there was
it didn't
any
cause
kind of
any
problem.
noticeable starvation or restriction in the downstream to superheater.
No.
Yeah,
No.
interesting.
There might, you might argue there could be like a audible change, because obviously now that's really in there to reduce the noise. And so maybe if you were taking measurements, but I bet it's one of those things where it's loud and then it's really loud. So it's still loud. I don't know, if you weren't really
Right.
measuring it precisely. But yeah, you might be able to recognize a frequency change or something like that. Yeah.
Okay. Kim Bachala has a question for Diedrich. He says they have a cracked liner that they've been monitoring for a few years. And so how did they remove the liner initially?
They actually, what they did is they cut a spool of pipe out just downstream.
Mm-hmm. Okay.
So basically made ourselves, you could argue, an access point with a spool of pipe.
And do you know how long they ran without that liner before you took it apart?
Oh, it was several years. I don't know the exact year, but it was several years that we did not have the liner in there. Yeah.
Okay.
5, 6. I can find out for sure, but it was quite a while.
Right.
Yeah, if I remember correctly, Adrian said like in 2011 they started removing them, and they commissioned in 2009. So they ran for about 2 years, and then they removed them all.
Right.
So.
And
Correct.
so the liner not being in there didn't cause any additional problems that they know of.
Well, the interesting thing is, typically I would argue the liner's there to maybe protect that downstream girth weld, but that's where I'd mentioned, they haven't seen failures at that weld, though they did see the failures here, but I think that's related to these massive quench events that are occurring that are dumping just massive amounts of water locally, and not necessarily at this weld, but this geometry all in here is getting stressed. Yeah.
Yeah. Okay. Barry, you have your hand up.
For Diedrich and maybe for Adrian, and follow on from the previous part of today's sessions. I wondered whether, and I'm really, as you guys know, only really interested in the erosion part, and not all this valve and temperature monitoring. But I wondered whether Diedrich or Adrian had this analyzed metallurgically.
We did not. And it's obviously just Diedrich here. I stole Adrian's headset, Barry. Sorry, I had to kick him off. So, but as far as, no, we just looked at it visually. I'm pretty sure we have remnants, but no, Barry, you're right. This was not sent out for lab analysis.
I'll tell you why I'm interested, because in these older HRSGs, the reheaters are not 91 tubing. The reheater 1 and reheater 2 on these are usually T23, and T23 is one of the worst materials for exfoliation of oxide. And I wondered whether that might have had any effect. I understand the moisture and the superheat and that sort of. I've listened to Bob enough, but I just wondered whether in this case there was likely to be anything from the T23 operating at quite high temperatures for 23 now, which we probably wouldn't do now.
Mm-hmm. That's a good point, Barry. I mean, we have T23 obviously in the reheater, right? So yeah, I'll dig into that. That's a good point.
And we've speculated that before of, it could be a 3-phase flow. It could be, steam, condensate, and solid particulate for sure. Would it be, instead of Augie, would it be like WAGI with water and oxide?
Yeah, it could be. Of course it could be, but you're not allowed to invent these names. Only us.
Barry, if you had samples of this erosion, could you identify if particulate was
Yes.
involved?
Yes. Yeah, you probably could, just from the morphology of the surfaces. I presume that Ori and his team have had some of these in this 718 material analyzed, but and then you could make a comparison. You wouldn't expect the same sort of damage if you had 91 in the reheater, I think.
Okay. If Efim has a hand up, can you unmute Efim?
Yes. Hi. Excellent presentation and tutorial. Be talking more to you about our valves, because we had our fair share of problems, not exactly the cracks that you're showing here, but a lot of other problems with bypass the superheater. One thing I wanted to mention here is we just replaced elbows downstream of the spray at the interstage hot reheat the superheater, because one developed a leak and the other we found with cracks. And when you look at the thermocouple downstream of the superheat, it located beyond the second elbow there on top, like vertically in the middle of the pipe. And we were seeing like 300-400 degrees superheat during any mode of operation, startup, shutdown, like change in load, steady state operation. So we were happy, 300 to 400 degrees superheat there at all modes. But when we started having those cracks and leaks, we put the thermocouples around the circumference of the downstream elbows, and we've seen some very interesting patterns there. So we are seeing water impingement on that elbow, even with when it shows 400 degrees superheat downstream of the spray. We are seeing a lot of water impingement, and its surface temperature goes all the way down to the saturation at any load, not just at startup and shutdown, but at those steady state conditions as well. So that was very interesting to me, and I guess we will also talk to you about modifying our spray pattern and spray the whole arrangement of the spray assembly there. So
I owed you a phone call, Efim, so I'll get on the phone with you later this week.
Yeah, this is something new that that you might not be aware. We just replaced those elbows just maybe 2 weeks ago. So yeah, it was a very interesting results. When I looked at that, I was just shocked how between the different parts of the pipe around the circumference, there is a 400-degree temperature difference. That was a very interesting thing. That's all I wanted to mention. Thanks.
I think Efim just brings up a great point, though, that all this data that we've done with Goreway was all from sensor data at the plant, so this was not adding anything external, but of course, there's always been people that have done what he's talking about, adding external thermocouples to be able to study. That can give us just that much more, input and information to run one of these studies. This 100 degrees C per minute is being measured, again, 75 meters away from the location. So yeah, you could even see massive changes. Now, I'm one that typically says when you put those thermocouples on, just be ready to see craziness, because I think nobody expects to see movement as much as that it will. But you can definitely look at it, and usually to me, it just shows me there's a lot going on or there's not. It's kind of interesting. We like to look at the plant sensor data to try to gain this information, because sometimes you get clouded by some of these thermocouple measurements, but they still give good data. They still can give you some really good information about what's going on.
These thermocouples on elbows downstream of interstage temperators or whatever. We've been doing that quite a long time, and you often see what you expect to see is that the inertia of the water droplets carry and impinge on the OD or the extra dose of the bend, and not so much on the intradose. So that's normal. Ori and I did a root cause for a client, one of his clients some years ago, and we had an array of thermocouples top bottom on each side of the straight pipe downstream of the temperator, and we saw some absolutely baffling impingement on the side of the pipe when the temperator started up. Ori was able to work out what was causing it, but some of the, when you start getting this more detailed instrumentation, as Efim says, it just baffles you sometimes what you see. We've got another question, Ori, back to bypasses. You mentioned cracking of the weld downstream of the desuperheater on the hot reheat bypass. This question is, can you say more about that cracking and what causes it and what the remedy is?
Sorry, say that again.
Here, but you mentioned it does happen often, right?
Yeah, at the downstream weld location.
Yeah, the girth weld downstream.
It's also getting let's say cycled by performance. So typically it can be a different type of signature. Sometimes it can be a water valve bouncing off the seat leading to that problem, or a lot of times in these bypass valves, it maybe goes back to the discussions in the first presentation. It becomes more of a weld geometry, weld quality combined with the thermal stresses. So we'll find some of these similar signatures, but if you have a really good weld geometry and good quality on it, maybe it can live up to it, and it's not the first thing to fail. Some of these other welds fail first, but if it had a bad quality or something with that weld, like we saw dissimilar metals, or which happens here too, we could have a 9 chrome desuperheater welded to a 22 pipe, with change in wall thicknesses. And so in those scenarios, maybe that's the first weld to fail. And so that's when that weld might fail, is because there's that added level of complexity of all these other unique things going on at that joint, where it just happened to be at Goreway that joint, this immediate downstream weld has not seen those problems. The problems were more, again, obviously internally, and then the welds right around the nozzle were getting more excited with some of these problems. So, but the data signatures are similar. And again, I say, we look for a lot of these, but each one becomes a unique issue where the geometry, the materials, the operation, again, it's that multi-prong approach. It's the hardware, it's looking at all that, but then it's how it's being operated. It's the combination of it all.
Let me make a comment before we get on with the rest of the questions. Is given the time, we've got so many questions, I don't think we're going to get to them all in the remaining time. So those of you that have sent chat questions in, if we don't get to you, we will get you a written response later. All right.
Have time
And
to
those
stay
that
on. I know
raise
that
your
might-
hand. If we don't get to you, then, send us the question in an email or the chat, or to Scott or myself or Barry, and then we'll get you an answer. Robert Torrance has his hand up for a while. Can you unmute and ask your question, Robert? Robert? Okay. How about Michael Amir? Can you unmute and ask your question?
And thank you for the presentation. I've got a couple of questions and also some observations. My reference is basically a coal-fired power plant, but in terms of what was presented with regards to the failures, we've seen similar. We've seen end cap failures, we've seen manifold cracking, etc. The one thing that we've observed is when after end cap failures, there is a noticeable difference in terms of vibration levels and noise around the area where the valves are located. My first question is, would IMI consider the manifold cracking a design issue or a plant operational issue? That's the first question. The second one, having seen what the pressure reduction tube or diffuser erosion looked like, were the valves trim basically also in the same condition? Because if you have that type of erosion there, then the expectation is also see typically the same erosion on the valve plug and the seat, and maybe the control cylinder.
I can answer the second question first. Oh, go. There's more. Go ahead. Yeah.
Yeah. And then
Well, let's
the third question.
Let's get these questions answered first, because we're already beyond time. So
to answer the erosion, there was definitely damage seen in the trim. So this is the trim that meets it. So there was damage seen in the trim for sure, and then also in the diffuser. But it's interesting because the diffuser was the major fail point, but the trim you can kind of limp along and then fix this as needed. But yes, so to answer the second question, yes, there was definitely damage seen from erosion to the trim. As far as the question about the water manifolds, I agree that the majority of this is more of a design, but I'll say that it's not necessarily just the valve design. It's also the piping geometry, because I've seen things where the connection to the bypass valve is very rigid without enough flexibility. So when that steam line starts to try to move during startup, it's being held too rigidly, and there's little that we can do to avoid just transferring those loads and moments into the manifold and causing problems. But yes, otherwise it is a design on our side. It's not as much operational, but you mentioned it's a coal plant, and I don't know if it's a supercritical plant, but definitely if you get to higher temperatures, we have seen operational issues where you can boil off the water in the manifold. If you have a really, really tight shut-off isolation valve on the spray line, you could potentially boil off the water and then really start to impose some thermal stresses on the manifold. And so that could be an operational link to manifold failures, but it's pretty unique if that's the case. I would definitely agree it's majority of the time the design of the manifold or the water piping connecting to it that leads, or just the geometry of the weld joint, the quality of the weld joint in the manifold, those types of things.
The other two questions that I had was, are you generally designing the diffuser to be within the spray arc? And then the last question is, if there is no issues with regards to condensate accumulation upstream of the valves, would you still recommend the Eurosolve trim? Thank you.
So the nozzle, yes, if you have no steam flow, the water would typically can see the diffuser. You know, the conical shape of the spray pattern could impact the diffuser, but that's the criticalness of making sure steam is always flowing to move it downstream. We have done things where we upgrade and we move the nozzles further away so that they won't have that chance of impinging on the diffuser. But of course, that's a cost issue. I'll always say that at the EPC level, you know, especially if it's 9 chrome and you're adding 2, 3, 4 feet to your length of your large 24 or 32 inch pipe at the outlet, that's a cost impact. And a lot of times compared to other manufacturers, we're all competing. You know, we want to try to keep the envelope small, but I definitely have done upgrades where we move those nozzles further away from that diffuser just to avoid any chance. Now, we still want to address the operational issues, but it's one of those where you can hopefully just make it more robust, you know. So definitely moving them further away would be great, but typically they are there. Now, there's another thing where you want them to be close so that you gain some of the flow profiling of that diffuser to help mix and atomize. If you do move them too far downstream, now you're just injecting into the larger pipe diameter with a lower velocity and you're not gaining as much atomization. So you have to do something about that. So typically we would put a liner in, and that liner would be there to reduce the diameter, speed up the velocity, and get the atomization back. So realize that the nozzles are close to that diffuser because they're in that gap region where there's a high velocity of steam to mix with the nozzles and get good atomization. So everything's a balance and a trade-off on that sense. In terms of the aerosol, you know, really you're typically, most of the time we're applying that when a customer has the damage. If you've seen the erosion, you're fighting that erosion. Typically it's a symptom of severe leakage that comes with wear of your seating surfaces. So most often we're applying that to somebody that has seen the damage. It's not so much that we're just across the board imposing that design on anybody if they haven't seen it. So that'd kind of be my answer to that. I mean, if you don't think there's any chance that you're ever going to have condensate going through your bypass valve, then there probably wouldn't be a need for the aerosol, you know, details and design. But if you believe you could, or if you've already experienced it, then it's an upgrade to your existing hardware to give you better shut off and longer life.
We're a bit over time, or you have time to answer.
I'm good. I'm good. If people are on, I've got a couple hours. I don't have a problem.
Well,
I'll just bill you. Do I send it to you, Bob, or who do I send the bill to?
Dietrich, go ahead.
I was going to say, I got a line up at the door here with the turnaround. So,
All right.
Well,
Well, thank you very much, Dietrich. Appreciate it.
all right. Talk to you guys
Good
soon.
luck. Thank you. All right. Okay. Zoltan Demoter, you have a hand up. Can you unmute yourself?
Thank you. Thank you for the excellent presentation. 2 questions. Have you taken samples of the fracture actually of the liberated end cap?
No.
Obviously, it was separated at the perforations. I would be curious to see what was the surface there. So there was no sample taken then.
No sample taken there, no. So and that would be something for Adrian or Dietrich to possibly look into doing, but no, there was no sample that I know of that was taken.
Mm-hmm. Another question, it is related to design. The velocity inside the diffuser just prior to exiting the diffuser.
The trim of the valve?
No. Inside the diffuser. So you have a steam velocity in the diffuser coming from the source, okay?
Yes.
And because it is a diffuser, you will have a different velocity there. So what is the velocity there at exiting the diffuser?
Exiting the holes, or in this region?
In the holes, you have critical speed. My question is, upstream the holes, what is your target speed?
I mean, it varies depending on different models and what.
But in this, because I see it's a pretty highly perforated yeah, trim. So I wondered what was the speed there in relation to
Usually we're
critical speed.
targeting something like a 0.5 Mach in that zone, but it also depends on, what the
Okay,
noise.
because it can
generally
also
is. Yeah.
depend on the actual operating
You're thinking
conditions.
you're thinking of like a valve wide open overload that
Yeah,
stressed it with
Yeah.
hoop stress or with some sort of shear that blew it off. Yeah. I mean, I think it's a combination of all those things. The erosion thinned it, the thermal stresses from the OD, and then yeah, it's under some pressure differential, and some loading, although it's not like it's not as high because these pressure drops aren't that severe. But yeah, it could be a combination of all those stresses.
Okay, I was just curious.
Mhm.
Okay, thanks.
Thank you. Simeonidis, I'm sorry if I destroyed your names. You want to unmute if you can and ask your questions. There's several pieces to them. Are you still with us, Simeon?
He just chatted in that the questions were answered.
Oh, okay. Thank you, Scott. Sanjay Sherakar, are you still with us?
Can you hear
Rob.
me?
Yes. Is that you, Sanjay?
Yeah.
I hear
So
you.
that's an excellent piece of work, Ori. Very
Thanks,
proud
Sanjay.
of you. Just two very simple questions. Is there a pressure transmitter downstream of the valve, but upstream of the resistor?
Yes.
Oh,
So
so
they have both up between the valve and the second stage diffuser and downstream. They have them. Yep.
okay. So that would be an indication that should help indication if the diffuser cap blows out, right?
Correct. In between here, they have this one, so you would see some change in the pressure drop basically between the system. Yep. We actually have seen that at a different system that has two-stage superheating that is experiencing some problems. Well, they're having an issue where something blocked the second stage, something blocked this diffuser, and this diffuser was getting less flow, so it was building up pressure. But I think if you lost the end cap at the valve, I don't know that we don't have you would still have the same pressure here, but I'd have to think about that.
You'll see change in characteristic from before and after.
Mm-hmm.
The second question is, how's the steam flow rate estimated for enthalpy control at Goreway?
They're using the pressure sensors and then using the resistor as a fixed flow device. So back pressure.
Okay, that should be very accurate then.
But what we found was that was being completely overridden. And if you had a keen eye, I didn't point it out, but you can see in this strip chart, this middle line is the spray valve position, and it just shoots to 60% stroke right at the beginning. And so that was the first indication that this was not being controlled by the enthalpy logic, because either there would have been a massive error in the calculation, but there should be no reason that the enthalpy logic would be driving the spray valve to 60% open so early, because flows would be so low. And that was the case. The enthalpy logic was calculating exactly what was supposed to be happening, which was just a very small opening and a very low flow rate. It was this massive spike that was being driven by that other override. So yeah, their enthalpy logic was spot on and doing everything perfect. It was never being given a chance to operate because this simple little logic override was just kicking it out and throwing it away. And basically they have a first stage spray system that's trying to control 50 degrees superheat all the time, just with this PID controller. And it doesn't even look at enthalpy control because this one's just overriding it all the time.
So this 50 degrees, there's nothing holy about it, is it? I mean, it could have been 100, 150.
Exactly. And that's why we mentioned the SNC Lavalin as the EPC in case others have that. or if anybody knows that they have this type of superheat logic, just be careful of it, because, and I've heard this in new construction discussions with clients that are EPCs building plants. They've talked about how they'll want to limit the superheat on things, and I guess I'm just very skeptical of that type of control logic after seeing this this type of behavior. So. But I agree, it could be 100C, it could be, and that was my, you know, Diedrich has dropped off, but one of the initial recommendations was just increase, it's a simple K factor. You know, you can see it, sorry, my arrow disappears. Oh, there it is. It's a simple K factor, 50C. I told them, try changing that to 150 just for one hot start and see what happens. You know, just increase it and see how the system responds, and then put it back to 50C if you don't want to do it all the time, but just test it. But they have some operation people that are a little hesitant to make changes, so they're going to take this in a much more systematic approach of you know, getting some process engineers involved to see what they can do. So,
Well, they couldn't make things much worse if they changed it, I don't think.
well, they have enthalpy logic that will control what I believe will be pretty well. So I would tell them you could just throw this away. So
No matter what it does, if you raise the value or eliminate that altogether, it won't be worse than what's already occurring, I don't think.
that's what I believe. That's what I believe.
Thanks, Ori.
Yeah, you bet, Sanjay. Thank you.
Thank you. Eric DuPont, are you still with us? If so, if you can unmute.
Yeah, thanks, Bob. So, yeah, excellent presentation again. Thank you. And I was just curious regarding the use of the OD piping thermocouples around the elbows. Yeah, what kind of what's your thoughts about how that actually reflects the ID temperatures, especially for the thicker main steam lines?
You know, all I can say to it is that you will see pretty rapid changes. So it definitely can you know, measure it and visualize it very quickly. So from the standpoint of, you know, how fast it conducts and how quickly it can give you a visual of what's happening. I mean, they respond pretty quick when I have seen them. But from the standpoint of, if you're asking, you know, exactly what the temperatures are and can you infer exactly what it is, I don't know. I could defer to Bob to answer that. Yeah.
Yeah, in the cases where we've used them, Eric, we're usually looking for transients. So I wouldn't dare attempt to do some kind of creep life assessment based on the metal temperature using the external, unless it was a very stable, steady state situation. But when you're talking impingement of water on the ID of the pipe, as Ori says, they show a dramatic change. And so
Yes.
really doesn't matter if it shows you 50 degrees C and it's really 75 degrees C, the damage is already done. And we know
Right.
which rabbit hole to chase down, you know?
Yes. Very good. Yeah. I
And they're
appreciate that.
so inexpensive that, you know, we're able to get lots of them on in the places we think we might want to see something. So it's not like we're having to put a drill and weld and do post-flow heat treat to put a thermal well in a pipe. We'd have to be very judicious and be darn sure we have the right location, right? If we're going to do something like that. But,
Yeah, we've done that multiple times. Yeah, so I appreciate that. And maybe like the thermal analysis programs maybe can help moderate what the ID temperature would be, I guess. And
within reason, you probably could.
yeah. Okay, great. Thank you.
Thank you. All right, Eric, I see no other hands at this point or questions. So Ori, thanks very much for a very, very interesting presentation. Thank all of you who participated and asked questions. Apologize